Good evening and a very warm welcome to expert speaker and participants joining us today. Once again, on behalf of the Department of Electronics Engineering, MITS Deemed University Gwalior, I feel honored to welcome you to the day 5th of AICT sponsored Atal Online FDP on emerging frontiers in quantum technology and communication. Once again, I request all participants to kindly keep their microphones muted and use the chat box for technical queries. For today's first session, we are pleased to have Mr. Arka Mukherjee, sir. Good evening, sir.
Yes, sir.
Uh,
Good evening. Good evening,
uh,
everyone.
a very warm welcome to AICT sponsored Atal FDP. Thank you for joining us. It is my great privilege and honor to introduce today's distinguished speaker, an eminent expert in the field of quantum communication system. Uh, Mr. Arka Mukherjee works as a scientist and team leader at the Center for Development of Telematics, that is CDOT, India, and is responsible for the hardware design aspects of fiber-based QKD system. He has over 13 years of experience designing embedded hardware for optical access networks and QKD systems. He is a gold medalist in Master of Science by Research from the IIT Delhi. He holds a bachelor degree in electronics and telecommunication engineering from well-known Jadavpur University, Kolkata, India. He has authored multiple technical articles in peer-reviewed international journals, technical magazines, and conferences. Dear sir, participants are looking forward to your talk. Please begin the talk.
Okay, sir. Thank you for the kind introduction, and it's my privilege to get the invitation from MITS to deliver the talk on introduction to quantum communication. So just let me share my screen first. Yeah. Okay. So I think my screen is visible to everyone.
Yes, sir.
Yeah. Okay. Okay, so today I will give an introduction to quantum communications and quantum key distribution protocols. I have another session tomorrow. I think in that I will go in depth on the QKD protocols, how the keys are being generated. And so I think today will be the foundation for tomorrow's lecture. And if you have any queries in between, please let me know so that I can address that as well in course of my talk. And just to give a brief introduction of CDOT, so CDOT is basically an autonomous R&D organization under Department of Telecom, Ministry of Communications, Government of India. Well, I am based in out of Delhi. We have two offices, one in Delhi and another in Bangalore. And we are mainly working in multiple technological domains, including 4G, 5G, wireless technologies, and optical communications. And also we are working actively in quantum communications for both quantum key distributions and post-quantum cryptography. And now, under DST, the National Quantum Mission is ongoing. So they have created four hubs for four quantum verticals: one for quantum computing, one for communications, one for sensing, and one for quantum devices. So CDOT is the hub jointly with IIT Madras for quantum communications as a and with for this NQM and for quantum communications. So to start with my talk, these are the basic outlines. So to first, I will discuss some basics of cryptography and why do we require quantum security at all, and what are the challenges that we will face once we have a quantum computers. Then I will talk about different dimensions of quantum secure communications because QKD is not only the only options for quantum communication. There are multiple other verticals as well, but QKD is always the most practical as of now. And then I will discuss more about QKD, how it works, how there are different network topologies, protocols, there are different standards that there for QKD and QKD networks. And then I will focus on basic challenges for deployment as well as development. Then I will come to your queries if any. So now we are using quantum technologies, but the quantum technology is not new per se because it has been there for more than 100 years now. And it is called that there was a fast quantum revolutions in the first half of the 19th century when we have the lasers, the solar cells, the MRI machines, so all these use some sort of quantum effects. For example, the lasers use stimulated emissions, the solar cells use photovoltaic effect, and the MRI machine uses magnetic resonance. And all these in the background, if you read all these technologies, there are some quantum phenomena underlying it. But now the thing is that it is called, we are entering into the, or we have already entered into the second quantum revolutions. The basic thing is that the basic underlying theory, the quantum superposition, quantum entanglement will remain same. But due to the advancement in components, advancements in technologies, we will have different applications in computation, communications, and sensing, so that it will have new use cases that were not there earlier. So it has very high potential to change our daily life and the science landscape. And keeping in mind of that fact, the United Nations has declared this year as the International Year of Quantum Science and Technology. This is just to mark the 100th anniversary of quantum mechanics and promotes its applications. So all over the world, the different events, seminars, webinars are being organized to celebrate this year of quantum. Now coming to the verticals of quantum technology, so as I highlighted earlier, it has four verticals majorly. So one vertical is called quantum computing that deals with extremely high speed computation. So once we have a quantum computer that is a full-fledged quantum computer, we will have a very vast application that are not currently not solvable. For example, drug discovery will be very much efficient because we can solve very high computationally intensive problems in a very less time. And we can have multiple applications in logistics, in financial markets, everything. But one downside of quantum computer will be that it will have the potential to break the existing classical encryptions. So one side we have a very bright future of quantum computing, but on the other side there is a threat that is arising out of quantum computing. And to counter that threat, the other field of quantum technologies, that is the quantum communication, comes into picture. So quantum communication is mainly responsible for securing our day-to-day communications. And there are multiple technological candidates, including quantum key distribution, teleportations, and ultimately quantum internet. So the quantum internet means today we are having a class internet in which the multiple computer servers are over connected over that internet. But in future there will be quantum computers and they will be connected over quantum internet, and that will be somewhat different from quantum today's classical internet. The third vertical is quantum sensing and quantum metrology. So that deals with ultra sensitive sensors. For example, quantum radar that can work in an area where there is no GPS signal. So it can lock once and it can go without it can run, that radar can run without locking with the GPS. And there are very high accuracy clocks, that type of application will emerge due to the quantum sensing. And the other fourth vertical is called quantum materials. So quantum materials is called like the thing is that we can have very low power, high density storage or very low power device and superconductors, and all the other three verticals will be the technology candidate for these quantum materials. So today my discussion will be mainly focused on the quantum communications. So coming to quantum communications, the quantum key distribution is the most practical application of is the quantum communication. So QKD mainly deals with the secure exchange of keys. It is not something related to your encryption. It is only something related to your exchange of keys. So many people confuse that QKD is encryption, but not. QKD is mainly responsible for secure exchange of keys. Those keys can then be used for encryptions. Okay. The second concept is called quantum secure direct communications. So quantum secure direct communication deals with the fact that using such quantum signals over a medium, for example optical fiber, we can actually transmit messages that are quantum secure. So that's why it's called quantum secure direct communication. So there is a Chinese group under Dr. Long. They are working intensively in the QHDC, but QHDC not much popular as of now, as many as so much popular as QKDA till date. The other vertical is other application area is called quantum teleportation. So in quantum teleportation, what happens? Suppose there is a quantum state in Delhi. Now I want to send the quantum state to Bangalore in such a way that that quantum state that is in Delhi will not leave its own place, but it will appear in Bangalore. So that's how the quantum teleportation works. So basically transferring a quantum state from one place to another, but without physically moving that quantum state. So that's how the quantum teleportation works. And the ultimate goal of this all this technology will be to create a quantum internet. So that will be an interconnection of the quantum computers, quantum sensors. They will talk with each other and ultimately form the quantum internet. That is the ultimate goal for all the quantum communication technologies. So today my talk will be mainly focusing on the QKD, because that, as I told earlier, it is the most practical application of quantum communications verticals. Now, coming to the basics of cryptography, you might be all aware that cryptography deals with keys, and the basic purpose is that we need to maintain the privacy and the integrity of the messages that we send over any channel. So, to start with the basics of cryptography, we have a plain text message. We encrypt it with a key using an encryptor. Then we transfer it over any media, that is by converting it to a ciphertext. The purpose is that any third party who does not have the legitimate key should not be able to decode that ciphertext. And at the receiving end, we decrypt this message to get the original plaintext message. Okay. Now, in any cryptography, it is very much needed that the keys should be protected from any adversary, because if your keys are public, then there is no security of your data. Now, how you do the actual encryption? There are two basic categories. You all are aware that one is called symmetric and another one is called asymmetric key. So what happens in case of symmetric key? We use the same key for both encryption as well as decryption. So we and that key lengths are smaller. Typical examples are advanced encryption systems or the data encryption systems. And the other type of keys is called the public private key or public key cryptography or asymmetric cryptography. So there are two keys. They are mathematically related. One is called public key and another one is called the private key. Now the concept is that data encrypted with public key cannot be decrypted with the only can be decrypted only with the private key. It cannot be decrypted with the public key. So that's how it works. But the basic concept is that this public key cryptography uh, can be broken once we have a cryptographically relevant quantum computers. So that's the main threat. Now, at present, how the system works. So suppose there is a two communication entities. One is in Delhi, one is in Bangalore, and they want to communicate. They want to transfer some data. So at first, they runs the asymmetric algorithm like RSA and Diffie-Hellman, and they does the key exchange. Okay. Then with the key exchange, both of these will parties will get the same key. Then they will do AES or some other algorithm to actually do the transfer of data, encrypting data. Now, why do we require this two-step method, first key exchange and then the actual encryption using symmetric cryptography? Because that asymmetric cryptography is a bit complex process. So you cannot actually encrypt the high volume of data using such algorithms, because that will be highly memory and time intensive. So to avoid that, we use the asymmetric encryption to exchange the keys, and then we use the symmetric cryptography to actually encrypt our actual payload data. Now, once we have a quantum computer, as I am telling that this asymmetric cryptography will be broken. How it will be broken, I will see in the subsequent slides. But once we break that asymmetric cryptography, then the key for symmetric key will be public. So our security will be compromised. Now the question comes, if asymmetric encryption is broken, what about the symmetric cryptography? But symmetric cryptography will not be broken. I'll see how it will not be broken, but we need to have we need to double the key length. So if currently we are using AES 128, we need to opt for AES 256. So that's how the system will work in future, because AES 128 will not be that much secure, and I'll come to how to go that way. So before going that, just see a basic quick overview of how that encryption really occurs. So this is that asymmetric cryptography. So A and B wants to communicate. So first they will exchange the public key over any communication media. Then A will encrypt the data using B's public key. Then it will convert to ciphertext, and then this ciphertext will be transferred over any media, say optical fiber or wireless, to B, and B will have it already having its private key, and then it will get the plain text back. So that's how the asymmetric cryptography works. Similarly, in the symmetric cryptography, you all are aware that once the key exchange is taking after the key exchange is take place after using the asymmetric encryption, both of them are having the same secure secret key. Then they use that same key to encrypt the data, convert it to ciphertext, and send it to B using the channel and decrypt it as the receiving end. So the only problem with symmetric encryption is that we need to have a prior key exchange. Now, what are the challenges in the present system that we are using? The major challenge is that the intrusion remain undetectable. So, if some attacker enters into our system and they are copying our data, we hardly get any alarm for that until and unless something gets out of hand or he publics made the data public. Then again, the other concept is that the security is based on assumption, and there it is not. It is based on some concept called computational hardness. So what is the computational hardness? So currently it is believed that these asymmetric algorithms are designed in such a way that even the most sophisticated classical computer cannot break this algorithm. So what is the basic underlying concept is that it is the prime factorization of a large integer. So it cannot be done in real time using a classical computer. But once we have a quantum computer that is sufficiently large, this type of assumption will not be valid. The other option is other challenge is that we can have brute force attacks. Brute force attack means we are trying all the combinations. Like if we have a 4-bit key, for example, we can have all zeros to all ones. So total 2 to the power 4 means 16 combination we can try. And if we have a quantum computer, this type of brute force attacks will also be very easy because it will have very high computational power, and it is very risky on the case is that if there is a very low frequency of key update. And as I told you earlier, that asymmetric cryptography by its design is 2 to 3 times slower compared to its equivalent symmetric counterpart, because there are public key and private key and the key lengths are larger. So that's the main reason asymmetric cryptography is slower. Now, to go deep into the challenge, like suppose there is a prime number, there is a number, we need to prime factorize that number. So there is for an example that we have taken a small number 72, and we can divide it like this 3 into 3 into 2 into 2 into 2. Then but if we take a large integer, the timing complexity of this operation is sub exponential. So the people from computer science background can know that sub-exponential timing complexity is less than exponential, but this is more than polynomial timing complexity. So sub-exponential timing complexity, due to this hardness, that today is our encrypted data is secure, and if any attacker or any adversary cannot break that encryption very easily when you are using the asymmetric cryptography. But once we have a quantum computer, there is a person called Peter Shor. So he has come up with an algorithm called source algorithm. So the source algorithm can reduce the timing complexity of that prime factorization problem of prime factorization of a large integer. From earlier it was sub exponential, now it can reduce to polynomial timing complexity. So that due to this reduction, these once we have a cryptographically relevant quantum computers, and just one thing, why am I telling repeatedly that cryptographically relevant quantum computers? Because not all quantum computers will be able to break this type of break this type of encryption or solve this much hard problem, because we need sufficient number of qubits. So at present it is not there, but there is a good promise that in future, in the coming days, in the next 4 5 years or 2 3 years, the cryptographically relevant quantum computer may come. So that's why I am calling it not a simple quantum computer, but cryptographically relevant quantum computer. So once we have that CRQC or cryptographically relevant quantum computer, that timing complexity will be reduced to polynomial timing complexity. Now, so once we have that timing complexity, that asymmetric encryption, the basic underlying concept that prime factorization cannot be done by a classical supercomputer will be broken. So our encryptions will be at risk. Now there comes another algorithm that is called Grover's algorithm. So Love Grover was a person. He was a pass out of IIT Delhi, and then he moved out of India. Then he come up with an algorithm called Grover's algorithm that also uses the quantum computer. But the concept is that this Grover's algorithm reduces the timing complexity of brute force attack from of the order of n to of the order of root n. So it also gains some certain speed due to this algorithm. Now it is the reason for which we don't recommend to use AES-120 it in when we have a quantum computer. So it is recommended to have AES-256, because the AES-128, the complexity of AES-128 will be reduced to AES-64, and AES-256 will be reduced to AES-128. But yes, then also it will be secure. That's why we recommend to use AES-256, not AES-128. So once we have a cryptographically relevant quantum computer, our encrypted data will be at risk, and eavesdropper can gain the information. And if your sensitive data like financial data, the government strategic secret are out, then it will be a very challenging time for us. So we need to prepare for that. So this is a comparative analysis of the different algorithms, their key lengths and their strength in front of a quantum computers. So the RSA has a strength of RSA 1024 to then RSA 2048 is electric craft cryptography 256 bit, electric craft cryptography 384 bit. They all will be reduced to zero. They all will be reduced to zero because just 1 minute. Yeah. They all will be reduced to zero, and you can see that AES 128 will be reduced to 64, AES 64, and AES 256 will be reduced to AES 128 because of the Grover's algorithm. So that's why we that public key cryptography or the asymmetric cryptography is not recommended, because their strength is equivalent to 0 bits of encryption, at all no encryption. But a symmetric encryption will be secure but with reduced strength. So this comparative table has been taken from the NIST report of 2016. You can have a look if interested. Now there is a professor in Canada. So he has come up with a good inequality that is popularly known as Moscas inequality. So this inequality states that when should we actually worry about the advent of quantum computers. So there is an this inequality has three parameters. So first parameter is the D. So D is called the amount of time for which we need to keep our data secure. So for example, each data has some lifetime. For example, your customer data, like the bank's KYC data, has a very long lifetime. Your personal health records has a very long lifetime. But suppose your defense secrets have a very long lifetime. But your OTPs have very limited lifetime. So D will be different for different types of data. Now T is the time that we need to transition from our classical system that is we are using today to future system that will be quantum secure. And it will need some time, because once we start migrating our network, it will not be done, it cannot be done in one day, it will need some finite time. So if we add that D plus T, it should be greater than or equal to the QC. So what is the QC? QC is the time by which a cryptographically relevant quantum processor will arrive, so that it can break that encryption. Now suppose your data lifetime is 5 years, and your like the time to migrate is 4 years, then 5 plus 4 is 9 years, and the quantum computer is coming suppose in next 4 years, so we are at risk. So that's how this Moscow inequality can be interpreted. And there have been many discussions on this inequality in multiple forums, and there has been a consensus between experts that we are already in the danger zone, because someone claimed that this type of problem has already breached in 2017, and we are today at the end of 2025. So this is the fact that we need to work hard to migrate our network from say classical to post quantum. The other thing is that there are multiple claims from technical giants like Google that they have achieved quantum supremacy or quantum advantage. Now, what is meant by quantum supremacy or quantum advantage? Quantum supremacy means you solve a problem that cannot be solved by classical supercomputer. So it is called quantum supremacy. Now, what is quantum advantage? Quantum advantage states that you solve some useful problem that is not solvable by classical supercomputer. So the subtle difference is that quantum supremacy means any problem that you can solve using a quantum computer that is unsolvable in classical computer. But quantum advantage denotes that you use some useful problem, like it is not some theoretical problem, but it is something related to your real life. So that is the basic the subtle difference between quantum supremacy and quantum advantage. Now, what is these claims? In October 2019, Google claimed that they performed a series of operations in 200 seconds, but they claim that if these operations were to be performed in a classical supercomputer, that would take 10,000 years. So they have reduced the 10,000 years of computing to only 200 seconds. A Canadian startup, Xanadu, in June 2022 claimed that they have done some similar tough mathematical operation in just 36 microseconds compared to 9,000 years of a classical computer. So this is a multifold gain in computing power. Then in October 2023, another company, Atom Computing, claimed that they have come up with a 1225 qubit quantum computer. And if you see all the technical giants again for Google, Microsoft, Amazon, and some Chinese companies like USTC, they are all working for quantum chips. So these are basically miniature quantum processors. So once they are investing so much in this technology, it is expected that in near future they will come up with some actually quantum processor that will be able to break that encryptions. So you can see that Amazon has the Ocelot, Google has the Willow, IBM Heron, Microsoft Mazodona. They are all these different types of, they are using different technologies, but all of these are quantum processors. Now, coming to quantum communication, there are mainly two verticals. One is called quantum key distribution, on which I will cover the next subsequent slides. The other thing is that called post quantum cryptography. Now, what is the difference between quantum key distribution and post quantum cryptography? So, quantum key distribution is basically a method of key exchange, and it is secured by the fundamental principles of quantum mechanics. So, how it is secure? Because in quantum mechanics, there is a principle that if you want to measure a quantum state, it will collapse, and it is the basic fundamental concept by which the quantum key distribution secures your key. So if you try to eavesdrop on the channel, the system property will change irreversibly and you cannot get back the original quantum state. So that's why QKD offers information theoretic security, because there is no assumption. Earlier in the case of public key cryptography, there was an assumption that certain mathematical problems cannot be solved by classical supercomputer. But in case of QKD, there is no such assumption. It is information theoretic secure. The other vertical is called post quantum cryptography. So QKD is basically based on the quantum mechanics, but PQC is a set of problems, a set of algorithms, and they are so hard problems that these problems cannot be even solved by a quantum computers. So they are quantum mechanics was quantum mechanics based. It is a hardware based solution. PQC is on the other side. It's based on hard mathematical problems and it is algorithm based. So these PQC algorithms are designed in such a way that they can be implemented on today's classical computer, but the classical computer means today's FPGAs or processors, but they will be impervious to attack from both classical computer as well as future quantum computers. So they are basically very hard mathematical problems, not solvable even by quantum computers. Now there is an organization in USA called NIST. So that NIST is doing the standardization activities through a competition type of things for these PQC algorithms. And recently they have finalized three algorithms. They are now called FIPS 203, FIPS 204, and 205. They are for this PQC stuff. So I am not covering PQC today. So my lecture will only focus on QKD. So if you are interested, you can explore how PQC works. So it is, and from the migration point of view, as PQC is software based, migrating to PQC for quantum security will be much easier. But quantum key distribution will require dedicated hardware setups, optical fiber or free space links. But as I told, PQC is algorithm based, QKD is quantum mechanics based. So in future, it might happen that there may be some chance that tomorrow some algorithms can be broken by some experts or by some modern future technologies. So we don't know that, but still till date, PQC is both QKD and PQC are used in different applications, and some strategic application recommends to use both QKD plus PQC. So again, coming to the basics of QKD, like how QKD works. So in QKD, it is basically a point-to-point network. We have two users. One is called Alice, and the other one is called Bob. They are connected using two channels. One is called quantum channel. You can see here. One is called quantum channel, and the other one is called classical channel. And as you can see, that quantum channel is unidirectional from Alice to Bob, because only Alice prepares some quantum states. It sends to Bob using this channel, and Bob measures it. So it is a unidirectional channel, and other one is called classical channel. So why it is called classical channel? Because it is a normal classical communication that is already there. So this type of communication taking place in this classical channel. Now, why there are two channels? So it will be more clear tomorrow when I explain how the keys are generated. But for now, you can assume that this quantum channel is for transmitting the quantum states from Alice to Bob, and classical channel is responsible some post-processing steps and some synchronization that is required between Alice and Bob. And the basic underlying concept is the Heisenberg uncertainty principle and no cloning theorem. So no cloning theorem states that you cannot copy an unknown quantum states. And you are all aware that Heisenberg's uncertainty principle, that you cannot measure two conjugate variables with certain without certain, like for example, position and momentum you cannot measure with certainty, both of them. You can either measure position or you can measure momentum of a particle with certainty. So there is some certain uncertainty involved in through the Heisenberg's uncertainty principle. Then the channels, this quantum channel and the classical channels, can be three types of channels are there: optical fiber, free space, or satellite. So satellite is basically an extended free space, but free space, there are terrestrial free space and satellite links. The first QKD protocol was presented by Charles Bennett and Giles Brassard. So through their name BB84, it is called BB84, and it was published in a conference in India. So that's the link with of QKD with India, because they are unable to publish that paper at that time to some foreign conferences. So they came to India, and there was a conference in ISC. They published that paper there. So it is linked to India in that sense. Now, if we see that cost of a data breach, so there is a IBM security report that is published every year. So in 2022, the average cost of a data breach was around 3.86 million USD, and it has increased around 25% to 4.44 million USD by 2025. So once there is a data breach, so it is a huge financial impact as well as your reputational impact and strategic loss. So we need to protect any sensitive data that is there in the network. And as I told earlier, QKD is a method of key exchange. I am repeating that again because it is not a method of encryption, it is a method of key exchange. And it is information theoretic secure because there is no assumption, it is based on quantum mechanics. And there are some market survey report that the global QKD market is expected to reach by around 3.4 billion USD by 2030. The report you can see, this is the from quantum technology, inside quantum technology report of December 2021. Now coming to how QKD actually works. So this will give you a overview how the QKD links works. So presently we have an encryptor and decryptor. So it takes the plain text message, then it converts to ciphertext, transfer it over any application channel, and in the receiving end, the opposite operation takes place, and we get back the plain text. So this is the existing network. This is your traditional or existing encryption system. Then when we introduce QKD over this network, we add an additional layer, that is the quantum layer. So in quantum layer, we have two modules, Alice and Bob. They are connected using two channels, quantum channel and bidirectional classical channel. Quantum channel is unidirectional, and together they are called a QKD link. Okay. Now, earlier they were using public key cryptography to exchange the keys between them. Now this encryptor will not use public key cryptography to exchange keys. Rather, it will request this QKD module to supply keys to this encryptor. So once the request come, their same key, that is for symmetric encryption, they will supply the same key to both encryptor and decryptor. So that's how a point-to-point QKD link works. So here the thing is that this vertical interface, that the key supply interface, is standardized by ETSI. I will name the standard is called ETSI GSQKD014. So the benefit of the standardized interface is that you do not need a vendor locked encryptor. So any third party encryptor who is supporting that standardized interface can work with any QKD systems. But till date, the QKD implementation is such that you need the Alice and Bob in pair, because one vendor's Alice cannot interoperate with another vendor's Bob, although the protocol may be same. So because there is some implementation related issues, so that in that sense interoperability is not possible, but any vendor's encryptor can work with QKD systems provided that this interface is standardized and it is as standards as per the ETSI standard. Now this is a point-to-point topology, but in real life network, this point-to-point topology may not be sufficient for all the applications. So ITUT has come up with different network topologies. So in CDOT we are working with different topologies. So one of them is called the trusted relay. So before coming to the topologies, is there any query till this point? Anyone? Then we can discuss if there is any query. Please write in the chat. Okay. So I'm continuing as there is no query. We can discuss that in the last also. So in going back to the previous slide, you can see that these Alice and Bob are connected using quantum channel, and I think one query is there. Yeah, what should be the ideal length of the keys? Madam, actually this ideal length of the key is AES 256, that is 256 bit key is recommended in symmetric encryption, because AES 128 will not be secure, will not be much secure when a quantum computer is there. So ideal length of the key will be 256 bits. This Alice and Bob generates the key continuously. When a request comes, it gives from that pool of key to 256 bits. So in typically it generates around 1 to 2 kbps rate, and it is gets stored in the memory inside that Alice and Bob. If a request come, it will supply 256 bits of key at once for AES 256 encryption. So AES 256 is the recommended encryption now. to have the quantum security. Yeah. Now this point-to-point link is connected by fiber. Each fiber link will have some loss, and in quantum communication, we cannot use amplifiers or repeaters because we cannot copy unknown quantum state because there is no cloning theorem. So the link length is limited by the loss of the channel. Now, how do we overcome it? Because suppose this link can run over 100 kilometer. Now I need to go 1000 kilometer. How do I go 1000 kilometer? Because one link cannot go beyond a certain distance due to the fiber loss. So to tackle this problem, the concept of trusted relay comes. So how does a trusted relay comes operate? So just assume there are three nodes: node A, node B, and node C. So node A has Alice, node B has Bob. So they will generate a key called KAB. Both of will generate a symmetric key called AB. Similarly, node B has another Alice and node B has a Bob. So they will also, as an independent link, they will generate KBC. Okay, so there are two links cascaded. Now, if node A is having node KAB and node C is having node KBC, then how do we communicate? Because no, KAB is not equal to KBC, but for symmetric encryption, we need same key at both the ends. So how it is done? So for this cascaded link, at node B we have both Alice and Bob, and at node B we have both key KAB as well as KBC. So we do an XOR operation that is called an one-time pad. So from the persons who are from the cryptography background, they will know that one-time pad is information theoretically secured provided the key length is equal to your data length. So KAB and KBC are both of equal length. So we do an one-time pad operation at node B because node B has both the keys, and we transfer this result of this XOR operation to node C using the classical channel. At node C, earlier we had KBC. Now again we will do another one-time pad or XOR operation. So KBC will cancel out from this equation and we will get KAB. So in this way, node A earlier had KAB, node B earlier had KAB. Now that KAB is now transferred to node C. So using that KAB, both node A and node C can communicate, and our effective distance of key distribution now increased from 100. Earlier, if it was earlier it was 100, now it has become 200. So that's how the trusted relay things occurs. Now why it is called trusted relay? Because there is a relay thing is happening here, and this node need to be trusted because the keys are there. So if the node is attacked, then your key will be public, your key security will be compromised. So that's why we in QKD we tell the concept of trusted nodes. So each of the nodes, Alice and Bob, where do we put the Alice and Bob, we call the nodes a trusted node because we need to ensure the physical security of the nodes. Because if there is no physical security, any attacker will not attack the channel, because attacking the channel is tough. There is quantum mechanics involved. He will simply attack your box, and going inside your box he can steal the keys. So we call we call the QKD boxes a trusted node. So this trusted node, using the trusted relay, we can enhance the distance of key distribution. Now using this concept, we can have a ring topology. The benefit of ring topology is that it gives high availability of keys. How? Suppose there are four nodes connected in a ring fashion. Now site 1 and site 2 is directly connected using an optical fiber, and they are generating some keys. Now due to some if cuts, the fiber between site 1 and site 2 gets cut. Now there is an alternate path that can be established for key generation from site 1 to site 4, site 4 to site 3, and then site 3 to site 2. So, and there is a clockwise path, there is an anti-clockwise path. So if the clockwise path is the fiber gets cut, we have an alternate path through using key relay, the key generation can work. So that's how the ring topology works. The other topology is called a star topology or dual star fail-safe topology. So the concept of star topology is that there is multiple Alice and there is a central Bob. So there is a optical switch is in between there. So the Alice generates the keys with the Bob in a time division multiplex fashion. So how does this operate? So first Alice 1 will generate keys with Bob, then Alice 2, then Alice 3, then Alice 4. So it will go on in a round robin manner. But what is the advantage of this star topology? The advantage is that the Bob node has the single photon detectors, and they are very costly and important items. So if you have a star topology, the costly Bob node is now shared by multiple Alices. So that's how the total cost of a network gets reduced. But the other disadvantage that will come for this topology is that the Bob becomes the single point of failure because it is the central node. If the Bob gets down, then the entire network will collapse. So to prevent that, the other concept is to have an active Bob and a standby Bob. So in normal operation, the active Bob will cater to half of the Alice, the standby Bob will cater to half of the Alice, And if by chance one of the bob fails, then the other bob will take over from all the Alices, and the key generation rate will get reduced, but at least the communication will work. So that's how the dual star fail safe topology works. So these are the basic some of the some deployment topologies, and we can also combine these topologies based on the requirement. These are the some basic building blocks. Now coming to quantum key distribution protocols, there are different types of there are different classifications. So one type of classification is based on the use decoding method of quantum states, and another classification is based on architecture. So based on decoding method is that the one is called quantum continuous variable and another is called discrete variable. So what is the difference? In discrete variable we deals with discrete properties of light. For example, polarization, that may be horizontal or vertical, diagonal and anti-diagonal, phase may be 0 or pi. And in case of continuous variable, in that we used to have quadrature of a quantized electromagnetic field, that may be an infinite values are possible. It is like an analog and digital systems. So if we have an electric field, we can have the moment that amplitude of the electric field can be infinite, like it can be 0, 0.1, 0.15, like that. Similarly, there are multiple values are possible. So it will, but in case of discrete variable, only certain values are possible. For example, in case of phase, it will be 0 or pi, and for polarization, it may be diagonal, anti-diagonal, or horizontal, vertical. So under discrete variables, there are certain types of protocol that is called distributed phase reference protocols. So in that protocols, we check the phase relation between two consecutive optical pulses. So that's why it's called distributed phase reference. Now, what are the examples? So continuous under continuous variable QKD, there is one called Gaussian modulated CVQKD, or GM's CVQKD, Gaussian modulated, and other was called discrete modulated CVQKD. So what is the difference? In case of Gaussian modulated, that electric field amplitude and phase that are all varies according to the Gaussian principles. And in case of discrete variable content CVQKD, there are some discrete values only allowed, but they are not actually discrete variable QKD. This is called discrete CVQKD. Then architecture of protocol, there are three types of protocol. There are one is called prepare and measure. How does it prepare and measure works? Because in prepare and measure, Alice and Bob is there. So Alice acts as the quantum state. It prepares the quantum state, and Bob receives and measures those quantum states. So it is called prepare and measure. So this is the simple diagram that I shown earlier, Alice and Bob. The other type of protocol is called measurement assisted. So in type measurement assisted protocols, there are three nodes. So in three nodes, so there are Alice, then there are Bob, and there are the third node. They are called Charlie. So in this case, both Alice and Bob becomes the transmitter, and Charlie becomes the central node, that is the receiver. So it is transmitter. It is also transmitter. Both of them are preparing quantum state, and Charlie is receiving and measuring this quantum states. And this protocol is designed in such a way that if this receiver or this detector Charlie is compromised, then also the security of this scheme will not be validated, because the final keys will be available only with Alice and Bob. So the measurement part is outsourced to third node, and the security is enhanced in such a way that if the third node is captured by an eavesdrop, then also the security of the protocol will not be compromised. So that's how it is called measurement assisted. The examples are measurement device independent QKD and twin field QKD. And for prepare and measure, the examples I'll cover in the subsequent in the next lecture. The BB84, coherent one-way, differential phase shift, all are prepare and measure type of protocol. And measurement assisted, as I told, MDI QKD, or measurement device independent QKD, and twin field QKD. The entanglement means QKD, the situation get reversed. So in that case, both Alice and Bob will receive, and the Charlie will become the transmitter. So in case of entanglement based. So Charlie will become the transmitter. It will have an entangled source here. It will send one part of the entangled particle to A and the other part to B, and they will become as the receiver. So only thing is that the role of Alice and Bob will get reversed in case of entanglement base from transmitter to receiver. And again here also again the third node do not have any keys. Only Alice and Bob will generate the final keys. So that entangled source will not generate any keys. It will only act as a source of the entanglement. So the examples are E91 protocol for EBQKD. E91, and named after the inventor Eckart. Now, how do we select a QKT protocols when we need to implement or design a QKT system? So there are multiple parameters that we need to consider. First thing is that some protocols are very good in on paper; they have a very good security proof. But when we come to actually physically implement those protocols, there are different challenges are there. So we need to check the whether that new protocol is actually physically implemented using the technologies that we are having. Then we need to consider how many detectors are required because these single photon detectors are very costly, so we need some protocols like prepare and measure require generally two detectors, but the measurement device independent QKD requires a higher number of detectors. So we need to check how many detectors are required because the cost will go up accordingly. Then what is the rate of secret key generation? Each protocol has some theoretical limit of how much secret key you can generate over a distance. So that we also need to check based on our requirement. Then each protocol supports certain distance. For example, coherent one-way and differential phase shift can go up to 150 200 kilometer, but on the other hand, twin field QKD can go much beyond around 500 kilometer. But they have some other type of complexity associated with that. So we need to make a trade-off in that sense. Then prepare and measure type of QKT protocols involves two nodes, and that measurement device independent and entanglement based QKT involves three nodes. So we need to consider that also. And there are some side channel attacks are also there. So that are called quantum hacking activities because this quantum mechanics is secure from theoretically secure, but the devices are not. So there are some side channel attacks exploiting the imperfections in the devices. So some protocols are immune from some of the attacks, some protocols are not. So while implementing those, we need to take into account like what is the immunity from various side channel activities. So as I told, during designing a quantum system, there are different choices. So first choice is the transmission media. So it can be either fiber based, that is the most commonly used. The other option is will be free space and satellite QKD. But the challenge is that these free space and satellite, they are highly dependent on the weather conditions. We need to have proper alignment between the transmitter and receiver, and their satellite based systems are also very costly, and the satellite comes for a very limited time during and when you generate the keys, and mostly the keys are generated in the night time because in the daytime due to the solar noise the performance is severely impacted. Then the for fiber based QKD there are two options. One is called the options with dark fiber. Dark fiber means you get a single dedicated fiber core to transmit the quantum signals. It gives the best performance, but it will be costly because you are occupying a full core. The other option will be to have the wavelength division multiplexing, like using the same code to transmit both your the quantum signals and your data on a same channel. But due to the crosstalks from the high power signals to the quantum signals, the distance will be severely limited. So it will we need to have a trade-off between the dark fiber and the multiplexing system. Then the other option is to have the what will be the wavelength of your quantum channel. So in 1550 nanometer, it is that is in the C band. It is the mostly used wavelength in that optical fiber communication because in this band the loss in the optical fiber is minimum. But we at this frequency band we use indium gallium arsenide single photon detectors, avalanche diode based. So these detectors have a lower quantum efficiency compared to 1310 nanometer. But in 1310 nanometer, there is a higher loss compared to 1550 nanometer in the fiber. But as I told, the efficiency will be better in the detector. The other option is 850 nanometer. That is not much very used. It is mostly used for free space links. So in this, there is a high loss in the optical fiber. But in that range, we have a silicon-based APD detectors. So that have very high efficiency. So 850 is mostly used for free space communication. In fiber, 1550 is the most used wavelength. 1310 is used sometimes because it has some immunity during multiplexing because the Raman scattering do not affect. Other data can be at 1550 nanometer, and the 1310 we can transmit the quantum signals. So that's how the things work. Now, for detectors, there are two types of detectors I'll cover in the subsequent slide. So there are two types of detector. One is called single photon avalanche diode based detector, and the other one is called superconducting nanowire single photon detector. So there are these are single photon detectors, both of them, but there is a subtle difference in the performance of both of these. So I will come by the parameters. So first parameter is called dark count. So dark count means when there is no optical signal incident on the detector, you will get some clicks due to noise. So this is called the dark count. So in case of SPAT this diode based detectors, you see that the dark count is around 800 counts per second, and for superconducting detectors it is around 100 counts per second. So it is much better. The date time is of the order of microsecond. So date time means once there is a click, once there is a photon incident on the detector, so it needs some time to reset the circuit and get ready for the next detection. So this time is of the order of microsecond for SPAD based detectors and of the order of nanosecond for the SNSPD. So it is much faster compared to SPAD. Then the detector efficiency is 10 to 30% for the SPAD and around 80 to 95% for this SNSPD. So you can see that all these parameters, like whether it is efficiency, jitter, everything is much better for SNSPD. But if you see the price is severely high because that's the only thing, and it is a bulky system. It needs cryogenic cooling. It operates at 2 Kelvin, 2.3 Kelvin temperature. It needs helium based cooling and a vacuum pump to operate with it. That is not shown in this picture. You can go to IDQ website and you can see how big is this. And on the other hand, these avalanche diode single photon detectors, they are commercially available from multiple vendors. CDOT recently has also designed one. So these are very portable system and they can go inside your box. So in most of the commercial QKD deployments, these SPAD based detectors are used, and where there is a research purpose or very high efficiency is required, mostly that SNSPD is used. So this is the difference between these two detectors. Now, as I told, each QKD system has distance limitations. We can get a key length. We can generate key up to a certain distance. It is called the critical distance. And if we increase the quantum channel length beyond a certain distance, then we will not get any clicks because all the photons will eventually get absorbed in the channel, and we will get only the dark counts in the detectors, and then the key rate will actually fall exponentially. So this region is not useful for any QKD systems. Now I will come to QKD standards. I will cover these slides quickly because these standards are evolving. So if you are interested, you can go to ITUT website and download these standards. And these standards basically cover how a QKD network should be designed, what are the basic criteria of QKD networks. And you can see that these Y.3800 to 3804 are the fundamental standards of how a QKD network should work. So they have defined different layers, like in the physical, we have the ISO OSI layer, 7 layers. They have defined 4 or 5 layers. I will cover in tomorrow what are the layers and how a QKD network should be designed. So these are the very good standards they have come out, and they are very lucid. Any person who don't have much knowledge of quantum, they also can understand this. If they have some networking concept, they can understand these QKD standards, and they are evolving. They are, till date they have come up to 3822, but these many study groups are also working to enhance these standards. Then study group 17 of ITU is also working on QKD network security and QKD network application security. They are also come up with multiple standards. So you can have a look if you are interested. Then ETSI is also working in this domain for QKD standardization. And as I told earlier, the most important standard is called the ETSI QKD 014. So this deal with the key supply from QKD to any application entity, routers or encryptors. So this is widely used, and other standards also deals with different QKD related aspects. Again, if you are interested, you can go and study these standards. Then ISO is also has come up with two standards. This is to actually verify the security of a QKD system. So suppose you have designed a QKD system. Now how do you actually verify that your implementation is secure? Because QKD is secure from the quantum mechanics part, but your implementation may have some loophole. So how to test that? So ISO has come out with these two standards to test the security of a QKD system. In India, there is an organization called Telecommunication Engineering Center under Department of Telecom. They have come up with a standard for QKD in 2022. It is called the TEC-GR 91000 generic requirement document, and there is a test guide for that same also. And recently, they have also come up with a standard for QRNG as well. That is the quantum random number generator. So this is the standard for TEC, and our CDOT's QKD system comply with these standards. Now, while developing our QKD systems, we need to take care of certain things because not all components we can choose. So first thing is that we need a laser. Why do we need a laser? Because we need to generate the quantum states, and there are no single photon sources available commercially that are of very high speed or good reliability. So to generate single photons, we need a continuous wave laser, and then we attenuate it such that each pulse contains at max one photon. Each pulse will contain at max one photon. No pulse will contain more than one photon. So that's how the QKD systems are designed, and we need a very narrow line with laser for that. Not every laser can work. Then we need an intensity modulator that are generally lithium niobate based, because we need a very high extinction ratio here. So these lithium niobate based extinction intensity modulators, we need to have a bias control for that, because we need to buy, this is the transfer curve of this intensity modulator, and we need to bias at a certain point. Generally it is biased at the minima, so we need to track that bias point. For that feedback control circuit is required, that is called a modulator bias control, or MBC. So we need these MBCs to actually stabilize that intensity modulator. Then we need a phase modulator that is also based on lithium niobate, and we need a proper synchronization between this intensity modulator and phase modulators. And this modulator requires some RF amplifiers because they are driven by the FPGA. FPGA drives typically of the order of millivolt, 100 millivolt signals. But this intensity modulator requires 5 volt, 6 volt of the order of this magnitude signals. So we need an RF amplifier in between the FPGA, then RF amplifier that will amplify, then this amplified RF signal will go to phase modulator for actually the modulation. Then, as I told, we need to maintain the mean photon count. We need a like variable optical attenuator and a photodetector to have a controlled circuit, so that we can set the actual mean photon count, like how many photons we need. So suppose we set mean photon number of zero point 0.5. So what does it mean? So if we see 100 pulses on average, out of that 100 pulses, 50 pulses will have one photon, and remaining pulses may be vacuum. So that's how the mean concept of mean photon count is there. So we need to precisely control the mean photon count, and in mean photon count should always be less than 1. Now the question comes, why should we have mean photon counts less than 1? Because when the laser is a Poissonian source, now when we attenuate the laser, and if we keep the mean photon count equal to 1, so there will be many pulse. You can calculate the Poissonian probability that if we keep the mean photon number equal to 1, there will be many pulses, and there will be a significant probability that some pulses will have more than one photon. But if you keep mu less than much less than 1, so for example 0.5 or zero point 0.2, you will see that the number of pulses with more than one photon will be severely reduced. The probability will be very less. Now, what is the problem with pulses with more than one photon is that if you are sending a pulses with more than one photon, any Eve or any attacker can keep the extra photon and send the other photon to Bob. So eventually he will get the same information as the information is Bob is getting. So the security will be compromised. So in QKD, the mean photon number is recommended to be less than 1. Again, we need to have proper synchronization between Alice and Bob, because we need to these systems typically run at 500 megahertz or 1 Gbps speed, and you need to properly mark the time slot, so that in which time slot you are sending zeros, in which time slot you are sending 1. So for that we need proper synchronization, and we need to synchronization of the order of picosecond level. So there are different companies. This synchronization protocol is not standardized. So different vendors implement different protocols. We have some patented algorithm for this synchronization aspect. Then at the bob, we will have a delay line interferometer or a Mach Zehnder interferometer. Again, this Mach Zehnder interferometer needs to be tuned properly, so that the time delay is exactly 1 bit. So some feedback control loop is also implemented for the delay line interferometer. So these are the challenges while we are dealing with QKD systems or QKD system development. We need to take care of this. So these all these equipment will be much more clear tomorrow, when I will show how actually these components, laser, IM, PM, are actually placed inside the QKD Alice box and Bob in delay line interferometer in Bob, so that they contribute to generation of the keys. Now I'll come to a slide. This is very important. Like, what are the practical challenges of QKD development deployment? So now suppose you have developed QKD. Now we need, ultimate goal will be to deploy in the network. Now while deploying in the network, we have from our experience we have seen that there are multiple challenges are associated. One of first challenge is infrastructural challenge. Is that I told you earlier that the best performance is with the dark fiber, that the quantum channel signals are sent over a separate fiber core. But all of you might be aware that in India, laying a fiber is a challenge, because you need to dig the road, we need to get permissions from different department. So and the total effort is very costly and time consuming. So you will not generally get a dark fiber in the field. So this is another challenge. And if you do multiplexing, then your distance will get limited. Then you will need to put the trusted relays frequently. So that is another challenge. So the major challenge is the lack of dark fiber. The second challenge is that the loss, more the loss in the fiber, the distance will be get reduced, because we can use amplifier. So in India, the deployed fiber are not very good in all the places, because there are multiple cards. because someone has laid a fiber, then a road construction starts, then the fiber gets cut, it gets then there is some patchwork is done in the fiber, and in this fiber splicing the loss get increased. So the fiber quality is not always good, and the other problem is that there is a rodent infestation. So in India, the rats cut those fibers in some places where there is no metal cladding, and then again the loss increases during the splicing. The other challenge is that the technology is that the SPAD, that diode versus diode based detector and the superconducting detectors comparison I have already shown you. So these detectors operate in air conditioned rooms, so it operates much below 25 degrees centigrade. So in the room, if in summer times the temperature goes above 45 40, so we don't we always require an air condition in India. So this is a challenge. And the third challenge is that these detectors, single photon detectors, are very sensitive detectors, and they can even catch the solar radiation from the sun. So what happens if there is a fiber link that is going in the air, and there is some open splice or joint that is not properly covered? So the fiber will catch some solar radiation, and that will get a click in as a dark count in the detectors. So that is very problematic for QKD systems. So we need to insert proper filters in the bob to prevent the other wavelengths, because these detectors are wideband systems. They typically offer works from 900 to 1700 nanometer. So to prevent those, we need proper filters. So that also adds to cost. The third thing is that each vendor has a proprietary implementation as of now. So as I told earlier also, so Alice and Bob must be from the same vendor. So there is no, again, there is no standard evolved for multiplexing of QKD systems. So how do you multiplex it? And there are some compatibility issues with the legacy encryptor, like the old encryptors. They sometimes they do not support those ETSI standardized interface for key fetching. So those encryptors cannot be readily upgraded with quantum security. The fourth challenge is that currently there are some certification available for QKD systems, but they are not in proper sense. They are actually security certifications. So if you implement a QKD system and there are some implementation related security loopholes, those cannot be really detected at this time. So these things are moving. So in coming days there will be security certification as well. But as of now, there is a lack and there is a gap in the field. Then other, there is no regulatory guidelines like which organizations should deploy QKD, when they should deploy QKD. There is no such guidelines from the government, but DST has formed a task force. They are coming up with a report in coming months. So I think that will give some clarity, like which organizations should migrate to QKD and which should migrate to PQC and at what time. Then in India, there is a shortage of workforce who are quantum literate. So that is another issue. But this national quantum mission has come up now. These type of problems are getting addressed. New universities are offering courses. There are multiple faculty development programs, awareness events are being organized all over the country. And there is a awareness, lack of awareness between all the stakeholders, including those chief information security officers, CISOs in different organizations, because they don't understand the actual problem. Why do we need quantum? Everyone is happy with whatever they are having today, but they are not actually bothered what will come tomorrow. So we need to prepare for tomorrow today, but that type of awareness is not available always. So these are the some challenges that we face. So these are the slides that I will share later on. These are in details. These challenges are described here. So I am just skipping because all these things I have already covered. Now coming to the last slide of this session. Now, as I told, like what is the myth versus reality? So as I told earlier, the first myth is that some people assumes that QKD and post-quantum cryptography is a method of encryption. So is that it is not a method. The actual reality is that it is a method of secure key exchange. For QKD, it is based on quantum mechanics, and the security is guaranteed by the principles of quantum mechanics. And for PQC, it is based on hard mathematical algorithms. That algorithms cannot be broken by classical supercomputer as well as quantum computers. Okay, and if you talk about the encryption, it will still be done by classical algorithms like AES-256. So we are only replacing the public key cryptography because that is not secure from a quantum computer, and we need to replace that. And there are two options: one is quantum key distribution, another one is post quantum cryptography. The other concept myth is that QKD is unbreakable. So QKD, from quantum mechanics point of view, it provides the information theoretical security. But as I told earlier, there may be some flaws related to implementation, because your code may have some bugs, your hardware may have some backdoors. So these type of things are not taken care by quantum mechanics. So we need to address those as well. So QKD is unbreakable is not per se true because there may be some implementation related loopholes. The other myth is that the QKD will replace all classical cryptography. So QKD will not replace all classical cryptography. It will only replace the asymmetric or public key cryptography, and it will coexistence with other classical algorithms like AES-256 and PQC as well. Because PQC will also come and with the algorithms that will coexist with QKD, and the most secure systems they will opt for both QKD and PQC together. So they will work in a fail-safe method. Like if QKD fails, PQC will take care. If PQC fails, QKD will take care. In that way, hybrid QKD PQC may also work. The other concept is that QKD requires quantum computers. So QKD has no relation with quantum computers. QKD safeguards your data from the threat that is being there due to the advent of quantum computers. And implementing QKD do not require any quantum computers. Implementing QKD will require your lasers, intensity modulator, single photon detector, delay line interferometer, these type of equipments. Then other assumption is that if we use QKD or PQC, it will eliminate all cyber attacks. So as you are till date, you have a got a flavor that QKD secures only the key exchange part. Then cyber attack can happen due to other reasons. For example, if your password is weak, or if you have some other issues like there is some design issue, design in the designing is not proper. So this type of attacks may still be there. So QKD is only securing your channel, because if someone tries to eavesdrop on the channel, the quantum state will collapse. So that's how the QKD will eliminate all the cyber attack. It will not eliminate all the cyber attacks in future, but it will definitely safeguard your channel from the attacker. So that's all from my for today's lecture. Tomorrow I'll cover in details the basic some basic quantum phenomena. Then some protocols that I'll cover is will be BB84, coherent one-way and differential phase shift, and I will cover in detail how actually the keys are generated in QKD. Then Dr. Mukesh had told me to cover the quantum random number generator as well. And if there is time permits, I'll cover tomorrow as the concept of QKD networks. So ITUT fast 4 standards 3800 to 3804. I'll cover how a QKD network looks like. So this will be the agenda for tomorrow. And now, if you have any query for from today's sessions, I can address that. I can see there are some
Yes,
questions in
sir.
the chat box.
There are some questions chat box. Yes, sir.
Yes. Uh, Yes, for ma'am has asked for that how many input qubits or photons should be used and Alice side to generate 256 bits. Ma'am, actually is that the qubits are generated typically at the rate of 500 megahertz or 1 Gbps rate continuously, and they are getting they are transmitted from Alice to Bob. Then some of the qubits are lost in the channel. Then some get registered at Bob, then the key generation happens. So tomorrow while I explain the process of secure key generation, you will get a clear idea. So the basic there is no such formula that this many qubits will generate 256 bits of key, because it all depends on what is the channel loss and what are the different parameters that are involved there. So you will get a detailed feel how the keys are generated tomorrow, and you will get a clear answer of your query. Some participants are doing their routine work and for oh, okay. Then what is the questions? Does or dispersion of fiber also play a role in QBR performance? Sir, actually, dispersion in fiber do not play much role, because we are using called very narrow pulse width. The pulse width is of the order of 125 picoseconds. So, but if you use a very long, because the length is limited to 150 kilometer to 200 kilometers. So, in this length, the fiber gets the pulse gets broadened, but that effect is not much severe. But for very ultra low, ultra high length QKD application, that might be a problem. But till date, it is not a serious issue. Dispersion. And another other thing is that the in QKD the laser that we use, that is very highly monochromatic. The line width is very less, as I showed in that showed in this slide. Just go back. So in this slide you can see that we need a line width of very narrow line with kilohertz. So the dispersion is minimized to that also. Yes. So what are the components that will be used to design a quantum communication at the transmitter and receiver? So at the transmitter, we will have laser, intensity modulator, phase modulator, variable optical attenuator, and photodetector. So how they are connected, I will show in the tomorrow, or if you are interested, I can show a slide today as well. Just let me go to that slide. Yeah, so this is a basic architecture of a QKD quantum communication system. So tomorrow in detail I will explain how these modules are interconnected and they work. So these are the basic elements: continuous wave laser of narrow line width, lithium niobate based intensity modulator. Then for attenuation we use a variable optical attenuator in along with a PD. Then we have a quantum random number generator QRNG, and everything is controlled by an FPGA. In the BOB side, we have a optical splitter and the single photon avalanche diode detector and delay line interferometer. Again, they are all connected to an FPGA. So how they operate, everything I'll discuss tomorrow in detail. Can you use a WDM system to design a quantum communication system and evaluate Q factor and Q and BRs? Okay. So, ma'am, it is not called Q factor, it is called QBER. QBER stands for quantum bit error rate. And you are right, you can use a WDM system. So, we have a WDM system. So, I will add a slide tomorrow like how the WDM system actually works. So, there is a fiber. So, we multiplex the quantum signals and the classical signals. But the only thing is that we need to attenuate the classical signal at the transmitting end in such a way that it only travels the distance of the channel. Then at the receiving end, we need to amplify that to reduce the Raman scattering. So that's how you can use the WDM system. We have published a paper also. If you are interested, I can share the paper link as well. But yes, you are right. We can use a WDM system to design a quantum communication system. That will be efficient in the sense that you do not need a dark fiber or a separate fiber core for the quantum channels. But the downside will be that due to the Raman scattering and other nonlinear effect, the noise will couple to the quantum signals and your distance will get limited compared to a dark fiber based implementation. Please suggest problem definition and research area in QKD protocols. Ma'am, that there are like there are under NQM we can see that there are different groups are working in QKD. So the basic problems are that some people are working on indigenous QKD protocol design. Like all these protocol, they are mostly they mostly come from foreign authors. So the some people urge that you can come up with the indigenous QKD protocols and along with a security proof, because without a security proof the protocol will not have much value. So this is an open area. It is true for QKD and both for PQC. In PQC also, all the algorithms are standardized by NIST. But for strategic applications, some people recommend that you come up with your own algorithms for defense and strategic use cases. So that will be a good research options. Also, you can research in the multiplex QKD system, because as I told, in India the dark fiber availability is very less, and it is very costly also. So you if you can come up with a very good quality multiplexing system that can work over a long distance, that will be also beneficial for and also that National Quantum Mission mandates to have 2000 kilometer QKD link over a multiplexed fiber. That in that also in that sense also it is also very important. Multiplexing of QKD is in the classical along with the classical data. If an optical fiber is used in quantum channel and the same fiber is used in traditional communication system, so how quantum channel is different from so I think you need to mean that how quantum channel is different from a classical signals. So quantum channel the power limit power level is very less. So you can get a typical idea that one pulse contains one photon, and if you get if you measure a typical power level, it will be around minus 75 minus 80 dBm. So this is a very feeble power compared to classical communication, which runs around 0 dBm or so. So there is a magnitude difference between the classical signal power and the quantum signal power. So that's why any noise coupling from the classical signals will severely degrade the performance of the quantum communication. And that's why it is recommended to have a dark fiber for a long distance operation. Please let me know if I am clear or if you have any further follow-up questions. Ma'am, then what is meant by multiplex QKD? Multiplex QKD means, ma'am, you are transmitting the quantum signals and your classical data, user data on a same fiber using wavelength division multiplexing. So different wavelength will carry different data. So one wavelength, say 1550 will carry your quantum signal, 1551 will carry your classical signal, 1552 will carry your data. So this is meant by multiplexing. Wavelength division multiplexing it is called. Same in a same fiber core, multiple wavelengths are sent. How do we determine whether to use entangled and single photon in QKD? For entangle based protocol, we need an entangled source. Like for E91 protocol or BBM 92 protocol, we need entangled source. And all other QKD protocols use single photons. But the thing is that today, as of now, the single photon source that are commercially available, they are not of very good quality or of very high speed. So the most common practice used to have a weak coherent pulse or an attenuated laser. So the laser is a coherent source. So attenuate the laser in such a way that the power becomes very less. In that is shown in this diagram. So we are modulating a laser then attenuating it. So that's why it is called a weak coherent pulse. So it is the most common source of single photon in commercial QKD systems. Which simulation software can be used to design QKD quantum communication system? Ma'am, there are some support is there simulation software, but they are not very much good for designing a link because they are still evolving. So I will send you some names tomorrow, but they are not of very good use. You can do some link planning or something, but they are not of very good use because RRI has come up with something called QKD SIM, Raman Research Institute. You can explore that, and there are some foreign simulators are also available, but they are not very good for doing some research purpose. You can explore OptiSim. I don't know whether they have added support for QKD, but they are not very useful for designing a practical setup. You can use MATLAB if you have some data, but they don't have any special QKD package. Any other query from anyone?
Okay, I think now there's no questions. Uh,
Sir,
thank.
tomorrow I will cover the algorithms in detail. I think the participants will be same tomorrow as well.
Sure, sir. Yes, sir.
Yeah, so I at that time I think they will get a more clear idea how actually the keys are generated because today I gave only an overview of the quantum
Yes,
communications.
sir. Yes, sir.
Uh,
Yes, sir.
and then tomorrow it will be clear how actually the keys are generated in QKD.
Okay, sir. Okay, sir. Okay, sir. Thank you so much, Mr. Mukherjee, sir, uh, for this interesting and very informative session on quantum communication. As a co-coordinator of this event, once again, I want to thank you for your kind support and participation in Atal FDP on emerging frontiers in quantum technology and communication. Thank you, sir. And sir, tomorrow we will meet again for the second session of your talk. Thank you,
Okay,
sir.
sir. Okay, thank you everyone for attending. And if you have any query, just note it down tomorrow as well. I can discuss that.
Okay, sir. And participants, we will now take a 10 minutes break. After that, we will begin the next session given by Dr. Satyendra Kumar Mishra from Spain.